big D. What am I going to do?
Put a big D on.
Put a big D here? What do I put here? We don't know yet, right? I have both a big C and a little c.
The big C will hang out with D.
Big C likes to hang out with big D, so therefore I put the little c here, right?
No,
No, where's the little c go?
it goes in the middle.
Here, right. Good, 2 different chromosomes. I have a big E and a little e.
The big E won't hang out with D and C unless forced, so big E is on the second one next to little C.
Good. Big E does not like to hang out, won't unless they're being forced to do it. So then I can put little e there.
Which forces the well.
So we got that there, I got a little c and a big E. Go back to your probability charts. Start at the top, work your way down the probability chart for the first little c, big E. Capital D. What is that? 14%. The other option is less than 1. So that's what we're looking. Pretty good chance that's the one. So now that's our Fisher race, genotyping. Now we have to do the minor. Big D, big C, little e. Do we have a big R or little r?
Big R.
How about this guy? Big R, little r?
Big R.
Okay? So now, does this get a 1 or a 2? Why? First spot after. Always make sure if you're doing these that this is the order they're in. Okay? Because sometimes in literature, they'll do them as like C, D, E. Because they're in alphabetical order. Okay? So just make sure that you put them in your brain in this order. Okay? What about this guy? R2. So my genotype is R1, R2 for the minor. Yeah.
So if in this circumstance, if little e was negative, would that then force big E to hang out with D and C? So that'd be the only circumstance, is if we had everybody was positive except for little e.
Yep.
That would force that.
Yep. Assigned seating by a teacher who's trying to get them to get along, right?
Is it walking?
No. Okay, good. Okay, so a couple notes, a couple of variants. There's a few variants out there we're going to talk about. Little f, it's actually little c, little e together. People, if you have little c, little e together on the same chromosome, which we know they kind of get put thrown together, what happens is there's enough overlap that you develop something called an anti-F about the overlap. So we almost always see them when they're on the same chromosome. So when we have R naught or little r together, we don't see them when they're on different chromosomes. They have to be together. It's not usually important unless the patient makes an antibody. People who are going to be most likely to make an antibody, Rh people getting a lot of O negative units of blood. Because they really, most Rh positive people don't have that little c, little e together. Right? This is only 4%? Yeah, 4% in Caucasian community. So most Caucasians in particular aren't going to have the little c, little e, and so they're going to get a lot of O negative blood. We know the most popular Rh negative is little d, little c, little e, and they can create an antibody to where they overlap, where the c and the e overlap. Okay, this is the story I told you. D and C are the popular girls, always sit together, never let E sit with them at the table unless forced. If C's gone, D and E are friends enough and we'll sit together, but she's a secondary friend. Okay, we're gonna skip the break because we already did it. So we have a case study. A patient with cancer of the liver has received numerous transfusions over the last 6 months. On 2/21/03, colorectal antibody other than ABO was discovered in the patient's serum. Received 2 units of red cells, warmed and cross-match compatible. On March 2nd of that same year, cold antibody was identified as an autoantibody, big I. Remember big I, all adults have it, so it's automatically considered an autoantibody. However, the antibody reactivity is still present reactive body temperature. Now we're in trouble. If it's just a cold, we don't care. But when it starts getting reactive body temperature, we worry. We'll get into all of this when we get into autoimmune lectures. Sample was QAS, quantity not sufficient. There's actually a Latin version of that, but quantity not sufficient for further workup. And so the patient was discharged without receiving any blood. That happens a lot. You'd be amazed how much you work on things. You work on these big things and they get sent home without even getting the blood you worked on. So they decided to take the phenotype of the red cells. They had plenty of red cells. So they took and they phenotyped the red cells. You can see they're an R, big R1, big R2, based on that. That should be something that in your brain you're just going to start seeing. Lewis, A negative, B negative, so we don't worry about those antigens. JK, A negative, don't worry about those antigens. We do worry about those antibodies, because you develop the antibodies for the antigens you don't have. This is all Greek to you right now. Starting next week, we'll get into the other blood group systems, and you'll start understanding these more. So a sample was sent to the reference lab for further workup. They did identify the anti-JKA, which is actually kind of a rare antibody. We don't see it very often. Pre-warned, cross-match was compatible with JKA negative units. April 5th, new antibody identified, and it was, once they develop one antibody, they tend to develop multiple antibodies. It just is par for the course. 2 JKA negative units and a Lewis A negative units were all compatible. However, one that was JKA and Lewis was not compatible, so like, great, another antibody we gotta work up because we know we've got this issue. All the Rh negative units were incompatible. So an Rh negative unit is most often little d, little c, little e. But if you remember back to their phenotyping, they have little c and little e. So it doesn't make sense. So the donor units, here's the patient. See, they had little c and little e. So the donor units that were compatible were these guys, but then these guys were non-compatible. As we look, we can see the ones that were compatible had no little c, but a little e, versus the non-compatible had both little c and little e. So probable genotypes, compatible units, the incompatible Rh negative units were likely little r. And so because of them, patient is F negative. So what when we're thinking about things like this, what I want you to think about is, so remember we got those squares, right? Big D, little d. C. How did they do that? Something along those lines, you know? Well, where the C and the E overlap, so if you think about how genes work, right? You got all these pairs of amino acids, and this is going to be, let's say, this is where little c is, and this is where little e is. Where F is going to be, it's going to develop something like that, like where it kind of crosses in the middle. Because they can't develop an anti-little c because they have little c. They can't develop an anti-little e because they have little e, but the F is kind of, think of it this way, it's like where they overlap. It's the two together. So the patient was determined it was not compatible to the F positive unit, so the patient is made an anti-little f. Weak D variants, running out of time. Weakly expressed D antigen. A lot of times what happens, they look negative at immediate spin. We let it go. If they look negative at immediate spin, we treat them as Rh negative and we give them Rh negative blood. However, with donors and with babies, we can't do that because Rh positive, if they had a weak positive, it could create a big problem. So what we end up having to do is run it through, incubate it, add this anti-human globulin, the green stuff in your rat, and look for a glutination for weak D. So weak D can be, anytime you see a weak D, so on one of your homeworks there's a column for weak D, that means they have big D. It's just not expressed as well for some reason. So when you're figuring out those homeworks, if the weak D column is positive, they have big D. We always do this on Rh negative donors to verify it, and Rh negative OB patients determine the need for Rh immunoglobulin, or babies. We do it for babies. We don't tend to do it for OB patients, because if they look negative, we're going to treat them like negative. Weak D, some of the reasons why it's weaker, fewer antigen sites than normal, so they're not going to react as much. Similar to the ABO subgroup, so there's fewer antigen sites for those. Any sort of a cancer affecting chromosome 1, remember anti-D or D antigen is on chromosome 1, so any of those cancers that affect that chromosome could affect it. Gene interaction between big D and big C. When big D and big C are sitting at that table together, big C is going to inhibit big D's expression. Okay? It's going to tone, big C tones big D down a little bit. And whenever there's a big C and big D together, they're always hanging together. So when they're together, you're going to tone down that big D. Partial D is another situation we may see, and what that is you can see, here's the D antigen, but it's like missing a piece. It's missing that little piece. Well, because of that, what if this person gets this D that has this piece, you can create an antibody to that little piece. So sometimes we have patients that look Rh positive because we tested for this piece here, but then they develop for the piece they missed. They develop an antibody. So I talked about that. I'm not going to do this case. Read through this case, though. It's really interesting. Pretty much reagents. The reagents at one hospital were one type. The reagents at another hospital were one type. And the patient was treated as Rh negative at one and then Rh positive at the next and developed an NID. Interesting case. G antigen is where the D and the C's overlap. We sometimes see this. The only people we ever see this with, the only people we don't see this with, I'm sorry, are that don't have big G antigen. They're going to be your little r, or little r prime, little r. You can read through anti-big G. It's not that big of a deal. We sometimes see it. It looks like D and C together, but when you actually break them down, it's not. So this is how people, if you have anti-DC, but you have D or C, it's actually probably going to be a G. I need to get through this because I have to get time. Other variants, CW is a variant, very, very low frequency. It is not an allele of big C, little c. CW is its own total different thing. V and VS are also low frequency. We actually see those more often in African Americans. This is a chart talking about unusual phenotypes. You sometimes get deletions in your genes where there's just no D. They look like D negative. They just get deleted. The Rh null I talked about. There's no Rh antigen due to some problem with your cell membrane usually. What's this one? The Rh null, similar to the null. When you're doing Rh typing, most times we're going to use monoclonal low protein reagent, in which case you don't have to routinely use Rh control. When you're using high protein reagents, you have to do the control. I get you the habit of doing the control just because for you guys it's that extra check. When you're doing in the hospital, when you're doing patients, anything, you can use any of your negatives as your control. False positive Rh test, patients with heavily coded in vivo with IgG or IgM antibody. Coded cells can agglutinate no matter what's going on. Anytime you have a false positive Rh, you suspect a false positive Rh, try washing some more. Maybe even chemically remove the antibodies because antibodies can cause problems. False negatives, super uncommon, most often caused by poor technique. This is why technique is so important. So we're going to be watching your shaking, washing your watching, all that kind of stuff. Too heavy of a self-suspension can cause a false negative. Failure to follow directions. If you don't add that second drop, you can get a false negative. Not doing a 37-degree incubation if it's indicated, or doing it if it's not indicated can cause problems. Or blocking antibody. Blocking antibody is like in babies, for example. Mom has so much maternal NID that it blocks those baby cells, so the reagent NID doesn't have anything to get to. So if mom has anti-D, we do see this on babies sometimes. They look like they're Rh negative, but in reality, they're Rh positive. It's just while mom's antibodies are coding them. Conclusion, Rh is the most important, it's most complex, it's important important for genotyping.